going on, guys? Let's look at this problem right here. Here this question is asking two homogeneous dielectric regions. One rho is less than or equal to 4 centimeter and two rho is greater than or equal to 4 centimeter. Have dielectric constants 3.5 and 1.5 respectively. If d2 is equal to 12 a rho minus 6 a phi plus 9 a z nanocoulombs per meter square, calculate E1 and D1, P2 and rho V2, the energy density for each region. Okay, now let's start with the A. A is asking to calculate E1 and D1. Okay, now in order to calculate D1, we have to know what is D1T is, and also we have to know D1N. Right, now let's see how we can find this one. First of all, we have to know that when we deal here, we are dealing with dielectric interface. So when we have dielectric interface, D1N is equal to D2N. Okay, and then D2N is what? D2N is, since they have mentioned the direction is only in the rho axis. Rho is less than or equal to 4, and this is rho is greater than or equal to 4. So this N is actually rho. So this is D2 in the A rho direction. So D2N is D2 in the AN direction. Since this is rho, N is rho, we can write this one as D2 in the A rho direction. And we have the D2 value provided, that is 12 A rho minus 6 A phi plus 9 AZ nanocoulombs per meter square. So let's write this one down right here. 12 A rho minus 6 A phi plus 9 AZ times 10 to the power of minus 9 in the A rho direction. But if you look at the rho direction, we only have 12, right? Others are going to be eliminated because we only looking for the rho direction. So this is going to be 12 times 10 to the power of minus 9, and that's going to be our D2N. D2N is going to be what? 12 A rho nanocoulombs per meter square. And we know that, so we have D2N right now. Now how to calculate D2T? D2T is basically D2 minus D2N. We calculated D2N, and D2 is the whole thing. D2 is the given expression, the whole thing. So if we subtract this one from the whole thing, that's going to give us D2T. So let's go ahead and do that. So this is going to be what? 12 A rho minus 6 A phi, that's the whole expression, plus 9 AZ, and subtract 12 A rho from that. 12 A rho from that, and we have to put nano because everything in terms of nanocoulombs per meter square. And if you subtract this 12 and 12, this 12 and this 12 will go away because this is plus, this minus. So we will end up with 6 A phi, right? 6 A phi, and this is negative, plus 9 AZ. Okay, and that is nanocoulombs per meter square. Now we have D2T. We calculated D2T. From this one we can calculate E2T, like we can create a ratio. Our purpose is to find D1. Now let's go ahead and create a ratio. We know that for dielectric interface, the electric field 2T is equal to electric field 1T. Okay, now electric field 2T can be written as D2T divided by epsilon R2, and E1T can be written as D1T epsilon R1, and D2T we just calculated right here. Okay, D2T is there. Now D1T we have to calculate, because if we calculate D1T, because we know that D2N is equal to D1N, right? D1N, so D2N we calculated right here. So D1N is already there because D2N is equal to D1N. We already have this part. Our purpose is to find D1 because the question is asking us to find out D1. We have to calculate what is D1T is. in order to calculate the d1, right? Now from this one we can see actually epsilon r2 and epsilon r1 are provided in the question. Okay, so here we go. Have dielectric constant 3.5 and 1.5 respectively. So this is epsilon r1 and this is epsilon r2. So we have both of them available, right? So we can go ahead and plug this one in this equation and find the final answer. So d2t we just calculated right here. That's negative 6a5 plus 9az divided by dielectric constant 2, that is 1.5, and also I have to put 10 to the power minus 9 right here because it's nano. That's equal to d1t divided by dielectric constant 1, that is 3.5. Okay, and if you rearrange and calculate this one, you are going to get d1t, that's going to be equivalent to negative 14a5 plus 21az plus, actually az, that's it, nano coulombs per meter square. So this is what we get from this one. Now we have this one. Now we want to find what is d1 is. d1 is what? d1t plus d1n. d1t plus d1n. And we just have to add 12a rho to this one. If we add, what's going to happen? We have here we have a5 and az, so it's not going to cancel anything. It's going to add up, and we are going to have 12a rho minus 14a5 plus 21az. So this is going to be the answer for the first question, d1. Now we have to find out what is e1 is. Okay, now as we seen before, we can use another equation. Let's get rid of this part. Okay, let's get rid of this one. Okay, now we are doing the same part, a part, but we are calculating e1 right now. Now e1 is what? e1 can be calculated using d1 divided by epsilon r1 epsilon naught. Now d1 we just calculated that one, that is 12 a rho minus 14a5 plus 21az times 10 to the power of minus 9. Okay, divided by epsilon r1 is what? 3.5 times epsilon naught is given by 10 to the power of minus 9 divided by 36.5, and if you simplify this one, you are going to end up with 387.8 a rho minus 452.4 a5 plus 678.6 az voltage per meter. So this is our E1. Now the next thing we have to calculate is P2. P2 is the polarization that can be calculated using another formula. Now let's get rid of this one. We are done with A part. Okay, now we are moving to the B part. Okay, now let's go ahead and do the B part. B part is asking P2 and rho V2. So let's go ahead and calculate P2. P2 is the polarization that can be calculated using this formula, XC epsilon naught E2. Now XC is what? FC is basically epsilon R2 minus 1. We already know epsilon R2, that is 1.5. So we can plug that one right here, and also epsilon naught here, and then we have to calculate electric field 2. So that can be calculated using this formula, D2 divided by epsilon R2 epsilon naught. From this one, epsilon naught cancels. We will end up with epsilon R2 minus 1 divided by epsilon R2 times D2. Now epsilon R2 is 1.5, minus 1 divided by 1.5. d2, we previously calculated that one. I erased that one, but this is the thing we got. 12 arrow minus 6a5 plus, actually d2 is given in the question, right? We calculated d1, d2 is given in the question. So 12 arrow 6a5 9az times 10 to the power minus 9, and if you simplify this one, you're going to get 4 arrow minus 2a5 plus 3az nanocoulombs per meter square. So this is the P2 value. Now we are going to calculate what is rho v2. Rho v2 can be calculated using this formula. Negative del P2. Negative del P2 basically 1 over rho partial derivative of rho rho 2. Okay, rho P2P actually, rho P2P, and then plus 1 over rho partial derivative with respect to phi, and then P to phi. This is rho P2 rho P2 rho and P2 phi, and then we had to, that's it, and also we had to do the partial derivative with respect to z. So that's only partial derivative with respect to z, P2z. Okay, now we just try to put the component of P2s. P2 have rho component, phi component, and also it has z component. So we just try to do plug that one individually and do the derivative. Now let's go ahead and do that. So this is going to be what we have, negative 1 over rho partial derivative of rho, and the rho component is 4 a rho. So this is going to be just 4 rho, because this multiplied by rho P2 rho, actually P2 rho is 4, and since it's multiplying by rho, we just have to multiply like this. Then the next thing exactly same as this one, we are going to have 1 over rho partial derivative with respect to phi negative 2 plus partial derivative of z with respect, partial derivative of 3 with respect to z, and after we compute this one, from this one you can see this negative 2 and these 3 are constant, so these two terms are going to be 0. This is the only derivative we are going to have. That's going to end up with negative 4 over rho coulombs per meter square. Okay, so this is the part B. So part B is done. Part B, this is second part. First part is asking for the P2. We calculate that one right here. Now let's go to the C. C part is asking the energy density for each region. Okay, let's see how to find it. Let's get rid of this one. The energy density for in region 1. Okay, let's go to the region 1. That can be calculated. The energy density can be calculated using this formula. Let's go to the region 1. Region 1 half epsilon 1 actually, and then E1 magnitude square. Epsilon 1 can be expanded as epsilon R1 epsilon naught, and E1, that's going to be just E1 which calculated before, half times epsilon 1 is given 3.5, that's the dielectric constant, epsilon R1 actually, so that's 3.5, and epsilon naught is 10 to the power minus 9, 36 phi, and then we had to put the electric field that we calculated in the first part. So that is equivalent to 387.8 square plus 452.4 square plus 678.6 square whole square, and that's going to give us 12.62 times 10 to the power of minus 6. Minus 6 means that's micro, so we are going to have 12.62 microjoules per meter cube. So this is going to be the answer, like for the region 1. Now let's go to the region 2. WE2, that's going to be exactly the same thing, half epsilon 2 E2 square. So epsilon 2 is going to be what? Epsilon R2 epsilon naught magnitude of E2 square half epsilon R2 E2. We can do another thing for E2. Instead of putting E2, we can put one more thing, like epsilon R2 epsilon naught. Instead of E2, we can put D2 divided by epsilon R2 epsilon naught square. So in that way we will cancel this epsilon naught and the epsilon naught, and also we cancel this epsilon R2 epsilon R2. So we will end up with this equation, half, so 1 over, and since this is square I cannot just directly cancel, one of them is going to remain, right, because this is a square. So I can cancel like epsilon R2 epsilon naught, this will be cancelled, like let's say this is square and this also square, so one of them will be cancelled and then others are going to remain, right? So we still have d square. So the final thing is going to be 1 over 2 epsilon r epsilon naught d2 magnitude square, and we just have to plug the values right now. So let's separate this one. So 1 over 2, this is epsilon r2, so epsilon r2 is 1.5, and then epsilon naught is what, 10 to the power minus 9 divided by 36.5 multiplied by d2 square. d2 square is what, d2 is given right here, we just have to pick up the first values and square it. So this is gonna be 12 square plus 6 square plus 9 square times 10 to the power minus 9 square whole square, right? So let's erase this one, whole square, and that's it. And after we square this one, we will end up with 9.839 times 10 to the power minus 6. 10 to the power minus 6 is micro, so it's 9.839 micro joules per meter cube. So this is going to be the WE2, and that's it. That's our final answer. I hope this helps. Thanks for watching.